Hi everyone, thank you so much for joining us today. Today we have a special guest speaker, Muhammad Uzair Khattak. Uzair recently completed his MS in Computer Vision from MBZUAI. During his master, he was working under the supervision of Dr. Salman Khan and Dr. Fahad Khan at IVAL lab. In this talk, he will present his latest research work titled as Broad Text, Prompt Learning with Text-Only Supervision. So without wasting any time, thank you so much, Uzair, for joining us today.
Yes. Hi, everyone. So I would also like to thank Ahmed and all the Cohere AI team for inviting me for this session. So let me just share my screen. Okay. So before we start, yes, I will just introduce myself a bit. So I am an incoming PhD student at Max Planck Institute for Informatics, where I will be supervised by Professor Bernd Schele. And before that, I recently completed my master's degree in computer vision from Muhammad bin Zayed University of AI in Abu Dhabi, where I was fortunately supervised by Dr. Salman Khan and Dr. Fahad Khan. So in my master's program, my main research focus was on the effective transfer of vision language models for downstream tasks for images and videos modalities. So the high-level goal is to fine-tune or adapt these multi-modal foundational models for video understanding tasks like action recognition, and for image recognition generalization tasks, which includes few-shot and zero-shot image classification. And I also worked on open vocabulary object detection during my master's. So let's start with the main topic for today's project. The title of the project is Learning to Prompt with Text-Only Supervision for Vision Language Models. So a little bit of background. So nowadays, we can see like foundation models are present everywhere. So we can call this era as the foundational model era as well. So these foundation models are typically pre-trained on large corpus of data. And this data is typically obtained from the internet. So maybe we can just do some simple web crawling to obtain such data. And in order to utilize this data, these foundation models rely on self-supervised objectives to do pre-training. The most common loss functions are contrastive loss or next token prediction. And popular examples of these foundation models include CLIP, GPT, Llama, etc. On the right side, we can see a high-level diagram of the CLIP multi-modal model, which consists of an image encoder and a text encoder. So the image encoder encodes the images to get the image embeddings, and the text encoder encodes the text captions for the corresponding images to get the text embeddings. During the pre-training of CLIP model, the goal is to maximize the similarity between the image and text embeddings, which are corresponding to each other. So for example, I have a dog and I have a caption that describes a dog. So my pre-training objective will be to maximize their embeddings. And at the same time, we want to minimize the similarity of the unmatched image and text embeddings. And this is achieved with the help of contrastive loss, which is employed by CLIP model. So what is the motivation to use such foundational models? So there are few like important reasons which I have listed. First of all, these foundational models are open vocabulary in nature. And this means that these models are not bounded by closed set of categories. Rather, any concept which can be interpreted in natural language can be recognized using these models. So they're not bounded by any closed set of labels or categories. Secondly, these foundation models are effectively transferable to downstream tasks. For example, this CLIP model, in the literature, people have used it in like array of tasks such as image classification, even object detection and image segmentation. So it is like highly transferable to various types of problem statements. And lastly, these models are highly generalizable, which means that a single foundation model can be utilized in like for many data sets without doing any fine tuning. So this is also their another good property. So the research goal is how we can effectively steer the behavior of those foundation models and adapt it for user-defined downstream tasks. For example, if I have my own data set and I want to improve my model performance, then how can I utilize these foundation models as the starting point, and how I can use like a training protocol to further improve performance on my own task. So the problem statement in this project is also that we want to steer clip for image recognition, or you can say zero-shot image classification. So as the very basic technique, clip can be used as a zero-shot classifier by default. And this is how the process goes like. So first of all, given a potential list of classes which we think might occur at the test time, we just curate the list, for example, plane, car, dog, etc. And then we wrap up each of the class name with a template. And the template can be very simple, such as a photo of a, and with the object, we replace each of the class name with the object. And then we use the clip text encoder to generate the text embeddings for each of the class name. So if I have n embeddings, it means that I have n class names in my problem. And now at the given test time, if I have a test image, I will pass it to the image encoder to get the image embedding. And now the classification problem is very simple. I will calculate the similarity of this image embedding with each of the text embedding one by one. And then I will select the class which has the highest similarity with the image. So for example, in this case, my dog is at the 3rd position, and this image also belongs to the dog. So this similarity with I1 and T3 will be highest. And that's why we will choose that this picture belongs to dog. So now let's dig more into this phenomena. So again, given a test image, for example, this is my image, which is a photo of a cat. What we will do in the classification, we will use a prompt, for example, a photo of a class for the all classes, including this cat class, and evaluate its similarity with the given image. So this is the main protocol that we will follow. So, and to calculate the similarity, what we will do, we will calculate the embedding of the text template, which is a photo of a cat, and then we will also calculate the embedding for the image. And then we will do their similarity, and it can be done like with simple cosine similarity. And in this case, we are getting like very high similarity. So the high similarity with the correct class and correct image leads to correct classification. And the reason for the high similarity is that the image content and the text content matches each other perfectly. Because in the image, we have a cat, and the template also describes a photo of a cat. So this leads to high similarity. Now let's look into another example, which is shown here. So now in the picture, we again have a cat in the image, but there is additional background and context and different attributes present. For example, the sea and the mountains. So in this case, if I again use the same protocol in which I use a photo of a cat, and then I do the similarity with the image in the embedding space, I'm getting very low score. For example, 0 points or 60% similarity score. So in this particular case, this could lead to incorrect classification. And because the similarity score for the correct class and correct template is very less. And the reason for this is that image content and the text content does not match very well, because the text template only says that it is a photo of a cat, but in the image, there is additional background context which is not defined in the text template. So how we can resolve this issue? We can perform textual prompt enhancement. So what does it mean? It means that with the given template, I can enhance my, you can say, text description by adding the relevant content which is described in the image. So for example, a photo of a cat near the lake. And then when I do the similarity with the corresponding image, my score again improves. For example, this time I'm getting 89% similarity as compared to 60% in the previous case. So the reason for this improvement is that image and text content now matches again. So from these examples, we have learned that the textual prompt enhancement is a critical aspect in improving the performance. However, there are some key challenges with this textual prompt enhancement. The first issue is that during inference, how we can design prompts that best describes the class at hand. So the issue is that we don't know what is coming in the test image. So similar to adding the phrase near the lake, improves results. So the question is what to add during the test time, because the image content is not known in advance. So we still want to enhance the prompt, but without looking at the image content. So this is the key challenge. So in order to solve, or you can say work on this idea, there are two branch of methods in the literature. The first branch is prompt ensembling via prompt engineering. This means that instead of using a single template, we will use multiple templates from different sources. This can be curated from humans, or we can use diverse captions which are generated from large language models. And then we do the you can say ensembling with these multiple templates, which have shown improvements in the experiments. The second branch is prompt learning. In the prompt learning, instead of designing the prompt manually, like we did in the previous example, we treat this process as a training process. So we treat the prompt as a continuous vector and optimize it with the help of supervised image label data. So in this way, we do not need to do manual prompt engineering, but rather use the deep learning training protocol, which is like the gradient descent and the whole training process, to automatically learn the best prompt that is suitable for a class. Now let's dig into more into these methods. So the first one, as described previously, is prompt ensembling via prompt engineering. So the main goal is that instead of using a single template, such as a photo of a class, we will use multiple templates and then ensemble their embeddings. So for example, we can curate multiple templates, such as a sculpture of a class, a bright photo of a class, or a painting of a class, etc. So the goal of curating multiple templates is that we want to cover all the content that can possibly arrive in the test image. So maybe the test image will be bright, or maybe the test image will be in the form of painting. So as I do not know the test image content in advance, I will just try to average all the possibilities beforehand. So this is a manual human-oriented approach for textual prompt enhancement. A second study in the same direction is to do the textual prompt enhancement, but using the power of large language models. So there is a recent work, QPIL, which has been accepted to ICCV 2023, which says that instead of using manual prompts, as we saw in the previous setup, we will use GPT-3 and try to get very rich detailed captions for each of the class. For example, if my class label is platypus, then I will query GPT and ask, what does a platypus look like? And the GPT-3 will give me a very enhanced or detailed caption for the class. And then I will utilize the simple or the same clip classification setup, the image encoder and the text encoder, but I will use the GPT generated templates in the text to produce the text embeddings. And this have shown to improve the results a lot. Just to give you an idea, this is like a result on ImageNet. So in the first row, we have clip 0 shot with a single template, which does not use any other templates, and it is providing around 66.7% accuracy. And if we use 80 templates, which was done in the previous case, different manual prompts, and then it improves the performance like around, I think, 1%, 68.32. But for the case of QPIL, which uses the power of GPTs or power of large language models to generate detailed captions, it provides like highest improvement in terms of performance. And for the ImageNet, it is providing around 69.65% against the manual prompt engineering and against the single template result. So this is the one branch of work which tries to do textual prompt enhancement, but there are some limitations in this setup as well. So let's look into them. So in the prompt ensembling via prompt engineering direction, the main, you can say, the best performing method is the LLM based method, which is QPIL. So the LLM generated prompts are class specific. This means that a caption which is generated for a cat cannot be reused for a caption of a truck. So if I have a label cat and a label truck, then I need to generate captions for each class separately. So a single LLM prompt cannot be transferred or shared among other classes. So this is one limitation, that I need to generate LLM prompts for each of the class one by one. Secondly, this method does not exploit the text data to automatically learn the suitable prompts. Because we are just doing the prompt ensembling, there is no optimization involved in this process. And thus, we are not fully leveraging the power of deep learning, which is all about optimization. So there comes, so next comes the second branch, which is the prompt learning methods. And as I mentioned before, instead of learning a manual prompt, we treat prompt as continuous vectors and optimize it with the supervised image label data. So there are like a lot of works which are doing the same kind of work, such as COP, COCOP, Maple. And the main essence is that instead of using a manual human engineer prompt, we will use like some vectors like V1, V2 up to VM, and then append it with the class name. In this way, we will freeze the complete clip model, and we will try to just optimize this learnable context. And how this optimization is done, the objective is that my training image embedding is similarity is maximized with my class name text embedding. So this is how my context in the prompt embedding space will be optimized. So just to give you an idea, for example, if I for the Caltech data set, if I use a manual template like a photo of a class and full stop, I'm getting like 86.29% accuracy. But if I utilize this automatic learning protocol, then and just optimize my different vectors and then append it with the class, then I'm like improving the accuracy a lot, and I'm achieving up to 83% accuracy. So again, there are several limitations with this setup. The first important limitation is that it requires annotated image samples for supervised training of prompts, because we saw that the images are required in the training process, and specifically labeled images. So this is one kind of challenge. The second issue is their biasness towards the few short samples used for training. So during the training, we have scarcity of data, and usually we are training in the few shot setup. So because of this, my prompts can overfit on the few short image features instead of covering the whole distribution of the data set. And because of this, it underperforms when we evaluate it on unseen classes or new data sets. So these are the issues in the second branch of method. So now comes our solution. And we basically propose a new framework, which is called as ProText. ProText stands for Prompt Learning with Text-Only Supervision. In summary, we are performing prompt learning without relying on images during training. So the goal is that we want to combine the merits of prompt ensembling, direction, and the prompt learning methods within a single framework. So just to see that how our method is different from previous set of branches, this table summarizes it well. So the first row shows like prompt learning methods, which requires images, but they can be transferred to unseen classes and data sets. The second class of methods are prompt ensembling methods, which leverage the power of large language models. So they are training-free methods, and this is and that's why they do not require any image. But unfortunately, they are not transferable to unseen data sets, because as we saw earlier, a caption for a cat cannot be transferred for a caption of a truck or a car. So in contrast to these stream of methods, our ProText approach at the same time does not require any image for training, but it is also transferable to unseen classes and data sets because it is a learning-based approach. So now let's get into more details. The main contributions are: we propose a text-only prompt learning framework for vision language models. Just to give you a history, previous methods on prompt learning are all image-based. Secondly, because we are only dealing with the text data, so we have proposed a text-to-text training technique, which is basically learning prompts for contextual mapping, which we will see in detail in the upcoming slides. And because of this text-to-text mapping technique, we effectively address the transferability issue of prompt ensembling methods. And this figure just like shows a high-level performance comparison for one benchmark, which we presented in our paper, which is cross dataset transfer setting. So the y-axis shows the performance average across 10 datasets, and the x-axis shows different methods. So we can see that ProText, which is like our main proposed method, shows improved performance across all previous methods. And some of the methods are image-based methods, and some methods are only prompt ensembling methods. So this shows the significance of this text-only prompt learning framework. So what is the main idea in our ProText approach? The main idea is text-to-text contextual mapping technique. So in simple words, ProText tries to learn a mapping function that maps a template with a simple text, for example, a photo of a class name, and it tries to transform or map this to a more detailed caption for the same class name. So this is the entire training objective in our approach. So more specifically, if my input template is a photo of a class name, then I want to transform this embedding into an embedding which is equivalent to the LLM generated detailed caption for the same class name. So indirectly, I'm learning a mapping function which performs textual prompt enhancement. And the mapping function can be learned via any training or tuning technique. For example, prompt learning, we can also use adapters or even use LoRa to fine tune the model. But we found that prompt learning works pretty well in our experiments. So we just use this as the main training protocol. So let's take it to the training protocol. So on the right side, we can see the main architectural diagram during the training. So just to give you a simple summary, we have like two text encoders. And the first text encoder, we have the class name template, which is the which contains a class name and a simple template such as a photo of a class name. And in this case, the class name is Persian cat. Then I will concatenate the learnable prompts, which are the only learnable parameters in the whole network with the vectors of this class name template, and then I will get an embedding, which is G tilde prime. And this G tilde prime is denoted as class name feature. At the same time, for the same class name, I will use GPT model, which is the large language model, and I will query it to describe the same class name in with a rich caption. So for example, I will ask, how does a Persian cat look like? Then I will obtain a LLM description for the same class name, which is like more detailed and more enhanced. And I will again pass it to the text encoder of clip to get the G tilde feature. Now my main training objective is that using these prompts, I want to learn a mapping that transforms G tilde prime to G tilde. So this is achieved with the help of contextual mapping loss function, which is a very simple loss, which is like mean squared error loss. So we are basically trying to minimize the distance between the prompted class name feature and the detailed LLM feature for the same class name. And during the training process, because this is happening for all the classes all together, the prompts basically learns to embed rich contextual knowledge in its embedding space. So the good thing is that once we are done with the training, these learned prompts can be utilized with any of the class name, irrespective of whether it was a training class or it was a new class at test time. So during the testing, we again plug back the image encoder, and we just use the text encoder, and we use the learned prompts which are trained in the first training stage. Then for the given class name, we just concatenate it and then perform regular classification. So and now let's look into more details about the benefits of this mapping function. So the first important benefit is that no k-short image labeled samples are required for training. So this entire process is only text-based. So we are not utilizing any images at all, which were being utilized by previous methods. At the same time, we are performing improvements over the prompt ensembling method, which is our main baseline in this work, which is the QPIL baseline, and we are showing or we are getting consistent improvements across different benchmarks. And lastly, the most important, you can say, advantage is that the LLM prompts, which we are only utilizing for the seen classes, can be transferred to unseen classes as well. And this is enabled because the learned mapper in the form of prompts is generic. It works for all the classes. So you just need to give it a simple template, and it will perform textual prompt enhancement for the same embedding. And because now we don't need the LLM prompts for the unseen classes, we are potentially reducing the prompt engineering cost by half. So these are the main advantages of our ProText approach. So now let's discuss the experimental setup. So particularly we conducted experiments across 4 different benchmarks. The first one is text-only supervised setting, in which we trained ProText using text-only data and show comparison with the different baselines. Then in the base to normal generalization setup, or specifically base to normal class generalization benchmark, we split each data set into base classes and novel classes. And then we just utilize the base classes in the training, and then we evaluate the model on the test set of the base and novel class. So in this way, we are trying to test the generalization of a method within a data set. For the third benchmark, it is cross data set transfer setting. So we are basically training ProText on the ImageNet data set as a source data set, and then we are evaluating it directly on other 10 new data sets, which are the cross data sets. And this shows the generalization of a method for new unseen data sets. For the domain generalization benchmark, we are again training ProText on ImageNet as a source data set and directly evaluating it on out of distribution data sets, which contains OOD samples. And these data sets are ImageNet adversarial, ImageNet sketch, rendition, and ImageNet v2. So now let's look into the exact results. So this is the first benchmark, text-only supervised setting. So here, the first row is the clip model, which just utilizes a single template. And for this, we are getting ImageNet accuracy of like 66.7%. With the clip attribute and clip 80, these are, you can say, different prompt templates, which we saw earlier. And it has shown to improve the results with the help of prompt assembly. So for example, clip 80 uses 80 templates for each class. Then the declip, wayfill clip, and QPIL are the LLM-based methods, which utilizes the power of large language models to improve the performance. And particularly, our main competitor is QPIL, which utilizes GPT prompts and performs assembling. So among this whole array of methods, the QPIL is performing the best. Now we show the different variants of ProText, because ProText can be plugged in with any kind of text data set. So the first comparison we can see is ProText attribute. So this comparison can be shown with the clip attribute at row 2, because both methods are utilizing the same text data, which are the attribute templates. And the difference is that ProText is using a training-based approach, while the clip attribute is just performing prompt assembling. And we can see that it shows improvement as compared to the clip attribute. Secondly, we also show the results on ProText 80, which uses the clip 80 templates used in the prompt assembling, where we show some slight improvements. Yes, and the most prominent results are obtained when we utilize the text data set of QPIL. So by just learning the prompts, we achieve the best possible accuracy in this benchmark against these baselines. So the summary is, with the same amount of text data, ProText improves clip performance against prompt assembling techniques by adopting a learning-based approach. Now this slide shows the results for base to novel class generalization setting. So again, just to recap, all the methods have access to only the base classes LLM dataset, because we are trying to directly see performance on the novel classes, so we don't have any LLM prompts available for that. So for the clip model, which just uses a single template, it has like lowest base class, normal class and harmonic mean. Then the QPIL, which is our main baseline, it shows improved performance on the base classes against the clip because it has LLM prompts available for that to do prompt ensembling. But its novel class performance is exactly same as clip because we do not have access to LLM templates for the new classes. So we just replicate the same numbers here. For the case of ProText, which enables the transferability of base classes towards the normal classes, we show improved results on the base classes, not that high, but our main, you can say, advantage can be seen in the normal classes, where we are improving over QPIL by around 2% or more than 2%. And these results are averaged across 11 datasets. And this also leads to highest harmonic mean of 74.9%. So the summary that we get from this benchmark is ProText enables the transferability of learned prompts to new classes and improves over the previous prompt assembling technique. Now comes the cross dataset transfer setting. In the cross dataset transfer setting, again, we are just training all the methods on the source dataset, which is ImageNet, and then we are directly evaluating it on the target datasets. So here we have divided different methods into 3 categories. So the first 4 set of methods are the methods that utilize labeled visual samples, which can be very difficult baseline because they are utilizing the images for training. Then the second category includes the zero-shot and prompt ensembling methods, which just utilize the LLM templates for textual prompt enhancement. And the third category is our version, which is prompt learning with text-only supervision. So we can see that when we train all the methods on ImageNet, the best transferability is provided by the ProText. So it shows like, I think, maximum performance in majority of the data sets and leads to the highest average accuracy of 67.23, which is average across 10 data sets. So if we compare it with the QPIL, which is our main realistic baseline, we are better than from QPIL around 2%, but also at the same time, the image-based methods, which explicitly uses images during training, we're also surpassing those methods as well in terms of performance. So this shows that a text-only approach can be also competitive to the approaches which explicitly uses images for training. And another thing that you might have noticed is that QPIL cross dataset performance is exactly same as the clip cross dataset performance. This is again because for the cross dataset, we do not have any access to prompts or any images at all. So we are just relying on the source dataset statistics or source dataset prompts. Because our ProText is transferable, it shows the improvements across the cross datasets. But for QPIL, it just cannot transfer the ImageNet prompts to unseen datasets. For the domain generalization benchmark, again, we train the methods on ImageNet and show it performance on the different out-of-distribution datasets, where again, ProText shows improvements on majority of the datasets against both the zero-shot and prompt assembling methods, and also the methods which uses visual samples. Now, we also conduct some important ablations to understand our framework much better. So the first table shows the ablation on the choice of mapping network. So as we saw earlier, that we are trying to learn a mapping function which transforms a simple template into more enhanced template of that same class. So we tried different tuning methods like linear adapter, MLP adapter, LoRa, and prompt learning. And we found out that prompt learning shows like competitive results. Also, the LoRa is also very competitive. So yes, this is the trend for different choice of different mapping networks. Then the second table shows the effect of performance, the effect on performance with different text data for training. And interestingly, we found out that when we train ProText with the GPT-3 data, which is employed by our baseline, we get the best performance. And we also tried some experiments using the prompts from open source models, such as the Mixtral model, which is just like recently developed. but it does not give as good performance as compared to the GPT based data performance. So this also shows that the future open source LLMs might cover this gap, but currently the closed source models of OpenAI are leading in the front. Lastly, we also see the ablation for the choice of loss used in the contextual mapping objective. So we observed that the mean square error loss is performing better as compared to the contrastive loss or the L1 loss during our experiments. We also conducted some analysis to understand how our ProText model is transferable to unseen classes or data sets. So the first analysis is the confidence score analysis. So in this study, we trained ProText on ImageNet text data only, and then we study its logit confidence for the correct classes in unseen data sets. So we pick 4 unseen data sets like DTD, Sun, Caltech, and UFC. And then we see that against the clip baseline, the ProText shows much better confidence scores for the correct classes. So for example, for the case of Caltech or UCF, we are getting like around better improvements, which shows that the prompts learned on the ImageNet can also benefit the classes of unseen datasets. And at the same time, for the incorrect class confidence, the performance should be lower, where also we show consistent trends. Secondly, we also visualize the attention map plots for the clip method and for the ProText method for cross datasets. Again, just to recap, for this visualization, we have trained our method on the ImageNet dataset, ImageNet text dataset. And we can see that for Caltech, DTD, and Oxford pets against the clip or QPIL, because for both we will get the same result due to non-transferability, ProText shows much better attention maps and focuses on key regions of the image or the class attributes. So this also kind of reveals that the ProText prompts are also better suited for unseen classes and unseen datasets, thereby improving its generalization. So to conclude, in this work, we have proposed ProText, which is a new direction to train clip using text-only data. Specifically, ProText employs text-to-text contextual mapping via learnable prompts. So this text-to-text contextual mapping is only used in the training, and it only requires the text samples. Also, the context learned by these prompts transfer well to unseen classes and datasets, and therefore we kind of address the key limitation of these LLM-based prompt learning baselines. And in terms of experiments, ProText shows improvements across 4 diverse image recognition generalization tasks. So the full paper and the code and pre-trained models are also available at these links. So you feel free to look into them. So yes, that's all for the presentation. So thank you very much. And if there are any questions, feel free to ask. Thank you. Okay, so I think the first question is by Anas Zafar. Is this approach class agnostic? Yes, this approach is class agnostic. So we learn a mapper for certain scene classes, and then we see that it can be transferable or it can be transferred to other classes as well. So just to like revisit, for example, in this setup, which is a cross dataset transfer setting, we see the ImageNet prompts. The ProText is learned using ImageNet prompts, but it can be also used to improve the performance on other classes. So yes, this is the main thing. And another thing is important, that to train a ProText, we need a data set which is a good representation. It should be a good representation, and it should cover diversity in its classes. Only then ProText can learn generic features. So if my source data set is also very limited, or you can say it does not contain much diversity, then it might also compromise my performance to unseen data sets. So second question is prompt learning. One is like making the prompts as closer as class it was from. Prompt learning one is like making the prompts as close as class it was from. I think it's slightly different. Prompt learning basically optimizes the context around the class. So if I have a template, for example, a photo of a cat, by prompt learning, I'm trying to improve the context described for cat. So a photo of a cat versus a cat that has 4 legs and it is furry and it has a tail. So this is what prompt learning do. It improves the context around the class. So it's something like that. And then no, right now I think there is no demo available on Hugging Face. So we are looking into it. So hopefully it will be there, I think, in the upcoming months. Yes.
I have a question.
Yes.
So, do you have any intuition on why the contrastive laws did not work as well as the MSc laws? Because originally CLIP uses contrastive laws to like maximize and minimize the difference between similar and dissimilar classes.
Yes. Yes. So I think we have the reason for this. So basically in our training set, which is text to text data set. So in a single batch, we can have multiple samples that correspond to the same class. So, but in our contrastive laws, we are not exactly, you can say, addressing this issue. So for example, if I have a batch of 50 examples in my training loop for the case of ProText, so these 50 examples, there can be, or there will be many cases that each text-to-text pair is also belonging to the same class, but contrastive laws will treat them as negatives. So multiple positives will be treated as negatives within a single batch for the case of ProText. But for the pre-training, it's the situation is slightly different. For the pre-training, we are using a data set which does not really which does not really like constrain that there will be multiple instances of a same concept. But for the case of ProText, we are using like a limited number of classes, right, during the fine tuning. So there can be case that a single so there can be a case that multiple positives will be present in the batch, but contrastive loss nature is different and it will treat them as negatives.
Yeah, right. Makes sense. Thank you.
No problem.
I also have a question.
Yes.
So first, thank you for presenting. I think it's an amazing work. So my first question is, there are some learnable vectors or parameters within the text encoder. So which part of the encoder do we learn? And the second question is, I also saw that you generate text. For example, if you give you give an LLM like GPT a text, and then it generates the text, and then you leverage the embeddings from that text to learn those learnable vectors. So what language model do you use, and do you have an ablation on how different models, GPT models or Llama 2 or any generative model, perform differently?
Yes. Okay, I got your question. So let me respond. So for your first question, let me just zoom in. So I think you are referring to these learnable parameters, right? Which is going inside the text encoder.
Yeah, right.
Yes. So basically, this is also, you can say, the prompt learning. It's not, we are again keeping the entire text encoder frozen. So all the parameters of the pre-trained model is as it is, but the input which will be coming into the text encoder, we will again just modifying the input itself with these again new prompts. So it is a variant of a prompt learning which is known as deep prompting. So again, we are just changing the input again. So we are not, you can say,
Right.
unfreezing any other layer or a projection.
So you mean what's coming out of the concatenation operation would be prepended with or appended with this?
Exactly.
Oh, okay. Okay,
Exactly.
now I understand.
Yes, in our case, we just replace it. So we just use these learnable prompts in the first layer. For the second layer, we will use these learnable prompts and we will discard the first layer prompts. So the length will be again retained as it is.
Right, right. So what is the rationale behind using this? I mean, we have different places as you're showing. We have two different places to prepend these two vectors. So why don't we use either of the two, or like why do we have to use both of them? Is there any
Yes,
rationale?
yes. So in my understanding, if we just utilize the all prompts in the input layer, this is a shallow version. But if we re-inject the learnable prompts in each layer of the transformer block, so this kind of tries to learn more complex, you can say, representations. So yes, so the main intuition is that we want to undergo learning even in the deeper layers of the encoder. So if I just utilize these prompts in the input layer, it will be only optimized, I think, based on the input context.
Right, right, right. And what about the so in I see in the so in the you have two layers like trajectories. In the below one, you are using an LLM called GPT-3. Is GPT-3 the one that you use, or the performance varies across different
Yes. So I
LLMs?
think that's your second. Yes. So that's, I think, your second question. So let's go into the applications. Yes. So I think we have performed this ablation, so in which we have replaced the GPT with different open source models. For example, we have tried the experiment with Mixtral, in which we generate the detailed captions from the Mixtral model. But from our experiment, it showed less, you can say, degraded results as compared to GPT-3. Then I think there's another LLM, Alpaca. It's one of the like earlier models. It performed even worse. So the performance really changes with different LLMs.
So these two open source, they have the same number of parameters. The model size is the same
No, I
as
think
GPT-3.
no, I think it will differ. So for example, this mixed trial, I think it's like 7 × 8, so it's like around 56 billion parameters. But for the case of GPT-3, I think it's even I think it's closed source, but it might be like more than 150 million or sorry, 150 billion or something.
Okay, okay, sure. Thank you.
Yes. So in my understanding, in the future, if we get more better, strong LLMs, then this gap can be narrowed down further as well.
Right. Yeah, that
Yes.
addresses my questions. Thank you.
Okay. No problem. Thank you.
If you don't have any other question, I think we can conclude the meeting.
Yes, sure.
Thank you very much. Really enjoyed the session.
Okay. Thank you. Bye.
Bye, everyone.